And so just to have a quick introduction, Yaniv is a PhD student in machine learning at Harvard University, and he works with Professor Finali Doshi Velez, which I think is a CBL alumnus. And he's at the Data to Actionable Knowledge Lab, or DTAC. He works on uncertainty quantification and tractable approximate inference for deep Bayesian latent variable models with applications in healthcare. So yeah, Yaniv, take it away.
Awesome, thank you. Let's see, can you all see my screen again?
Yep.
Great. So yeah, thank you for having me here today. My name is Yaniv, and I'm excited to be here and present work trying to understand failure modes of variational autoencoders and how these failures basically impact your downstream tasks. The work I'll be presenting today is done in collaboration with Wei Pan and Finali Doshi Velez. And like Andrew said, Andrew and David came to our lab a couple weeks ago and gave a talk about the really awesome work understanding what happens, what kind of pathologies you get for Bayesian neural networks when you perform mean field Gaussian approximation, which made me realize that we actually care about very similar problems, right? But I've been working just on a different model. And so hopefully y'all will find some of this work relevant. Like Andrew said, I'm broadly interested in models and inference used for real decision making in safety critical applications like healthcare. And specifically what I care about understanding is whether your model and inference are going to have the right theoretical properties that you need for your downstream task. I do work on a number of other like in addition to variational autoencoders, I work on predictive uncertainty, modeling heteroscedastic noise, and generally latent variable models. And so I'm excited to talk with y'all maybe after for whoever is interested about any of these things and hear more about what y'all are doing. But for today, I'll be focusing on VAEs. To motivate a lot of this work, I'm going to start with some of the clinical data that we work with in our lab. So the data set that I've been personally working with so far is data from an in vitro fertilization clinic. So the goal is you have a couple and you want to help them have a baby. And so for this data set, we have a couple of questions like, can we model the core cohort of people likely to have a live birth versus not? And can we somehow characterize this cohort with a low dimensional latent space that is human meaningful, like maybe have a factor corresponding to like some underlying unobserved disease or some other broad health of the patient, et cetera. And so for this data set, the question that I started out with is, is a VAE appropriate for this task? And so just keep this in the back of your head, and at the very end, we're going to come back to this question. I'm assuming most of y'all are familiar with variational autoencoders, so I won't spend a lot of time going over the background, but I will just briefly mention it. So VAEs are these models that are, they're jointly used for basically two things, density estimation and representation learning. And in the literature, they're used for a number of downstream tasks like generating synthetic data, learning compressed or low dimensional representations or disentangled representations for semi-supervised learning, etc. And how they do this is basically as follows. You pose a simple distribution over a latent space. In this case, we're going to call P of Z, often assumed to be Gaussian. And then using a complex function, usually a neural network parameters by some parameters theta, we decode or generate from this latent space. We add some Gaussian noise, and that is how we get samples from our observed data, X. Now, for this model, the goal is to maximize the likelihood of the observed data, but this is intractable. And so what people do instead is they introduce this second model, the inference model, Q of Z given X, which is supposed to approximate the posterior of the model. And then what you do is you basically train both of these models jointly using a lower bound known as the ELBO. And so this lower bound is still actually hard to optimize, but what makes it easy to optimize is a convenient choice of your variational family. And so what often people choose is a mean field Gaussian or MFG, which is just a Gaussian. with in this case, the parameters are going to be predicted using a neural network. And this neural network, or this Gaussian, is going to have only a diagonal covariance. So the question that we're going to try to answer here broadly is, what are we sacrificing by using this approximation? And more broadly, how do you know if your VAE worked, if your VAE approximated your data distribution well, etc.? So typically, or in many cases in the literature, right, VAEs are used to model image data sets. And image data sets are convenient because you can actually just use a lot of gut checks to figure out if your VAE did a decent job, right? For example, if you're supposed to be modeling chairs, you could print out samples from your, you could generate samples and you could look at them and be like, yeah, that looks like a chair. I've done a good job. But when you have numeric or EHR data, you can't do the same kind of gut checks. You also can't evaluate the probability of a given data point or a subset of data points very easily, because if you could, then you wouldn't need that lower bound. And lastly, like, this is a continuous distribution over a high dimensional space, and so interpreting P of X is not that useful either. And so how do I know that my VAE worked well? Existing work basically focuses on a couple problems, but the one that I think is motivates the bulk of the work is basically saying, like when you use this lower bound, there's a gap between the lower bound and the log likelihood you try to approximate. And so this motivates having tighter lower bounds so you get better approximations. And so there are approaches that basically propose really interesting solutions to this, but at a cost to either having high like more expensive computation or noisy gradients or some other non-trivial thing to understand. And generally in the literature, something that I felt has been lacking is good data sets that really show me when a VAE is going to fail, with kind of like the basic settings that make it so easy to train, so easy to implement, etc. And so in this work, we basically focus on this. So we're going to focus on the Gaussian prior and Gaussian observation noise for a VAE, and a Gaussian or mean field Gaussian variational family. So the most kind of popular instantiation of a VAE. We're going to be focusing on global optima of the ELBO. So I'm trying to understand, regardless of what optimizer you use, how good could the approximation be? And lastly, we're going to be proposing a bunch of these benchmarks that I hope future researchers are going to be using when they propose new inference methods, to basically try to answer two questions. One is, when should I use these fancier VAE variants? And how are my downstream tasks going to be affected by my choice of mean field variational family? As a broad outline, I'm going to start with a toy example of a failure. I'll explain to you why it happens, and then I'm going to try to build intuition generalized to the case where I'm dealing with like a very common instantiation of a VAE where the model is very flexible, can express any function. And then lastly, we'll look at effects on downstream tasks. Oh, and this work comes from two papers that are up online in case you want to look for more details. Oh, and then one last thing before I get into the toy example, because we're interested in global optima of the ELBO, which is completely intractable, we're going to have to get something that's close to it, or at least we believe is meaningfully similar. Because for any kind of meaningful toy example we can have, you absolutely cannot get the global optima of the ELBO. And so the way we're going to do that is, for each of the example, when I show her, when I'm like, this is what a VAE learned, I mean that I ran it with 10 random initializations, 5 starting at the ground truth generative model plus the best corresponding inference model for that ground truth model, and then 5 random restarts with a totally random initialization. And we're going to select the ELBO with the model with the highest ELBO to see what the ELBO prefers. And we're going to fix the hyperparameters at the ground truth to make sure there's no model mismatch. So I'm basically going to be saying, like, I generated data from this model. Can I recover it? Can I recover the data distribution? So let me start with a very simple example. In this example, we have our latent space again. It's just a simple Gaussian. Observation noise is a Gaussian. And then our likelihood is this funky formula over here, where basically we have just a matrix really applied to the Z plus the observation noise. And so here our function is linear in Z, but nonlinear in the parameters. We're going to treat A as the model parameters and B is just some fixed constant. And the question is, if I pose this model and then I use a mean field variational family, maximizing the ELBO, will I recover the ground truth distribution? And for this model, the answer is no, you will not. Here's the ground truth distribution. It is a correlated Gaussian. Here's what the model learns, or the global optima of the model, and it's a totally uncorrelated Gaussian. So by trying to learn this model, we basically missed the only important thing about this data set, which is the correlation. So why did this happen? This happens for a fairly simple reason. Turns out that you can write the ELBO actually as a sum of two objectives. The first objective's goal is to basically match the learned data distribution with the observed data distribution. And then the second objective is matching the approximate posterior with a true posterior for that model. And so if you look at the objective as sum of these two terms, let's see what happens at the ground truth. So at the ground truth, we know that the first objective has got to be 0 because that's the model that generated my data. So that KL has to be 0. But the second term for this model is actually quite large. And the reason for that is because my likelihood is linear in Z, my true posterior is a Gaussian. For this model is a correlated Gaussian. And so when you approximate the correlated Gaussian with a mean field variational family, you're really missing, important features of that posterior, right? Which means that that term is going to be really large.
I'm sorry, can I ask a question?
Yes.
Yeah, just to clarify, are you using a neural network as your decoder or using just a linear layer as your decoder?
I'm using, sorry, I should clarify this. I'm using exactly this model. So I'm literally saying this is my function, and I'm going to try to learn, I'm trying to maximize the ELBO with respect to A.
Right. So can I interpret this as a VAE, but with a single linear layer for the decoder? Like,
It's
is it something like that, or?
it's even more restricted than that. So this is like a linear VAE. So your likelihood is linear, but I restrict my likelihood to be only lower triangular matrices.
Okay. And for the encoder, you're not actually using an encoder. Are you just doing the optimization like individually, or are you doing
So
amortization?
I think for this one I did do amortization, but I can go ahead and double check. The results are going to be the same either way. It might be
Okay.
a little worse with amortization, but it should basically give you the same result.
Okay. Cool.
So yeah, so this is basically this is a model with a restricted likelihood.
Could I also ask a question here, Yaniv?
Sure.
I think this is a really interesting example, and I think toy examples like this are definitely a great way to get to the bottom of these things. But naively, I mean, maybe this is related to this special structure that you impose, that you multiply everything by AA transpose. But naively, I'd have thought that if you had a linear model like this, that you could learn orthogonal latent variables in the latent space that affected, orthogonal directions in the observed space. And then the posterior would be independent for the two, and it would factorize, and then you would be totally fine. So when I've run experiments like this in the past, I actually find that the optimal mean field solution corresponds to the PCA solution, where it finds orthogonal components, rather than learning this like manifold where if you rotate the latents, it doesn't affect anything. So why is that not happening here?
So the difference between the difference between this and like a probabilistic PCA or a linear VAE is the fact that I've restricted this to be like a diagonal matrix. So normally with a linear VAE, what ends up happening is technically the model is non-identifiable if I were to just look at the generative model, right? I could take my latent space, I could rotate it in any way I want, and then I could apply transformation to it. But when you perform inference, your VAE is going to select a specific rotation, not the ground truth rotation, for which you have a
There is no ground truth. I mean, yeah, it's unidentifiable, so it doesn't.
Exactly.
Like
So it's going to select the rotation that makes your overall transformation from latent to observe not have a correlated posterior. In this case, what we've done is we've effectively taken away solutions for which you can have that. So basically what happens here is we've constructed a solution for which there is no, any function that generates your data well is not going to have a mean field true posterior that can be approximated for it. And so what ends up happening is you end up finding an optima for which you have a smaller posterior matching objective and a smaller maximum likelihood objective. So what this means is this basically means that you've compromised learning your data distribution. Did I answer your questions?
Yeah, you did. I think so. So the sort of the particular parameterization you use with this Cholesky of AA transpose is sort of set up in a way to couple these things, so you don't get back the trivial, you know, the more trivial solution.
Exactly.
I always thought it was quite interesting that running a mean field VAE on a linear model gave you back the PCA directions. I thought, as a, you know, because that's kind of an interesting justification for PCA, and then that links to like this disentanglement literature where, you know, a bug in our variational method is giving us orthogonal components even though our model didn't care.
Right.
And so, like, is this really the right way to go for disentanglement? It seems like a very strange argument.
Yeah, it totally does. And this is something we do have later an example of like what happens when you do disentanglement. That's also very basic, but maybe it would be interesting to talk with you about. So yeah, so basically what happened here is we restricted F so that every model that explains P of X well is going to have a non-mean field Gaussian posterior. And so now you're forced to trade off. How much do you want to explain your data well? How much do you want to capture your posterior well? And we get an approximate P of X that's actually quite bad. And by the way, the reason why you might care about what it means to restrict the function class is because if you are able to specify a meaningful class, a meaningful prior in a sense on your generative model, right, then your latent codes that you learn are going to become more meaningful, as opposed to just being the thing that is most convenient for the VAE to learn, like in the linear example that we just mentioned. So now the question is, okay, I just created an example for you that has non-mean field Gaussian posteriors. Does this always correspond to a global optima that's bad, that gives you a bad, causes you to capture P of X badly? And specifically what happens in more common uses of VAEs where your function is this deep neural network and it's totally unrestricted. So that's what I'm going to focus on next. So far I've given you this example. I'll explain to you broadly the mechanism that's going to cause for these pathologies. And now I'm going to try to answer these questions by focusing on a 1D example in which we relate properties of the prior and the likelihood to the posterior, and take it from there. Okay, so if I have a non-mean field Gaussian posterior, am I always going to have a bad global optima? Let me try to give some intuition using this very simple toy example. So in this example, what we've done, and I'm sorry that axis labels are a bit small. I have here my likelihood function. So this is the z-axis. This is the x-axis, x without the observation noise. And I just have this quadratic that describes my likelihood. And over here, I've got the corresponding generative model I'm going to use. So the z is going to be drawn from a uniform distribution for simplicity. And then we're going to decode our latent space using our quadratic function and add some noise. And that gives us this joint density. So I sample again a z on the bottom here. I translate it to be in the middle of this curve. And then I add some Gaussian noise around it. And that's what gives me my joint distribution. Over here, you can see I have my marginal over z, so my uniform distribution. And over here, if I project the distribution onto this axis, you see that I get my P of X, my density. So by looking at these 1D examples, the reason why it's useful is because we can actually very clearly relate properties of the function or the joint distribution to the properties of the posterior. So if I take a cross section over here, a horizontal cross section, you see that I intersect my joint distribution in two places, which means that my posterior is going to have two modes. So for many of the points here, I'm going to have a bimodal posterior. Very difficult to capture with a mean field Gaussian because you necessarily miss half of your distribution. So you'd expect maybe for this distribution, we're going to have a trouble approximating P of X. But as it turns out, for this distribution, you would have absolutely no trouble approximating P of X. And the reason for this is because actually there exists a much simpler function that captures P of X and has a nice kind of Gaussian looking posterior. And so let me show you how this happens. So in this, if you remember, like projecting onto this axis, onto the x-axis gives me a P of X, right? So if I look, for example, at this region over here, there are two regions that contributed mass to this. There's this region over here, this kind of tail, and then there's this region over here. But there's no reason that these two regions in this example need to be on two separate, corresponding to two separate z's. I can consolidate, in fact, the mass contributed over here and just put it all over here. So what this would mean is kind of like chopping this quadratic in half and then folding it over. So what I get is I can actually construct a likelihood function that's exactly half of this quadratic, but stretched. So now instead of spending half of the time here, half of the time here, it spends all of its time only on one side. I get this distribution. And so when you project it, I get exactly the same density. And if you look at a cross section for this distribution, you see that it intersects my mass in only one place. And so my posterior is really unimodal. So that's quite nice. The VAE managed to find a simpler solution, recovered P of X quite well. And I do want to notice that it didn't recover the true function, of course, which may have implications on your downstream task. So for example, if your Z represents, let's say low Z represents one disease, high Z represents another disease, but these two diseases, in fact, when you observe them in a patient, you observe them having the same symptoms. So both Z's decode to having the same X, right? This is the model that you would want to use for that patient population. But what this example shows is even though you'd be able to capture the data distribution well, this VAE is going to have an inductive bias towards a different model that is not your ground truth model, for which these two types of patients won't get two different representations in latent space, but really the same. So that's just something to keep in mind.
Can I ask another question?
Sure.
So on the right-hand side, you're trading a VAE with a uniform prior, which is the ground truth prior on Z as well. Is that right? Okay.
Yeah.
But the posterior is Gaussian for the VAE.
The posterior, so I think for this example, I used maybe a beta distribution, but you should be able to use a clipped Gaussian or truncated Gaussian if you want, probably get even better results.
Cool, thanks.
Sure. And so in the same way that I've made the simpler function to have a simpler posterior, I can actually also make it more complex. So if I take this curve and I just, I shrink it in half and double it, right? Now I've created a joint distribution that has, again, the same marginal over X. But again, if I intersect, if I look at a cross section, now I'm intersecting it at three places. And so my posterior is going to have three modes. So we have this non-identifiability property here, right? Which is quite interesting. So what are the takeaways from this example? No, having a non-mean field Gaussian posterior for your ground truth model is not actually always problematic. Because the ELBO is just going to find a function with a simpler posterior if it can. And another thing to note again is that like it's going to have an inductive bias towards non-ground truth models potentially. So your latent space that you learn may not be that useful for your ground stream task, but at least for generating data, it seems to be pretty good. So the question is still, when will VAE inference approximate my data distribution poorly, right? And so here what we're getting at is that we need to find some sort of ground truth model for which the posterior needs to be non-mean field Gaussian, even for the simplest function possible for your data. Which kind of says something about the minimum complexity of your joint distribution, right? So like if I have my Z sampler from a Gaussian and I have my X's that I've observed, right? Basically what I'm saying is like any function, the simplest function that I could use to map my Z's to my X's needs to be sufficiently complex or have a sufficiently interesting looking posterior. So how do we get that? That's exactly what I'm going to get into now. So basically what I'm going to do is I'm going to give two conditions under which this happens, and I'm going to show you broadly how to use these to construct these data sets. And then we're going to kind of try to generalize from these how these data sets manifest in real data sets as opposed to synthetic data sets. And then lastly, I'll get into downstream tasks. Okay, so when will the ELBO approximate P of X poorly? So it's going to do it under two conditions that are kind of straightforward from the demonstration that I just gave you. So the first condition basically says the true posterior needs to be difficult to approximate with a mean field Gaussian for many of the x's that you have. So you have to look at a high density region of your plot. And in that high region of density, you need to have your P of z given x be difficult to approximate. And then second, there can't be a simpler function that approximate P of x well and also has a simpler posterior. So these are the two conditions, and they might be still unintuitive, but I'll show you later how to use these to create data sets that create problems for us. And I do want to note that under these conditions, the VAE will never approximate P of x perfectly. And I think a lot of the literature is concerned with, can it approximate it perfectly or not? How big is the gap? Here, what we're more interested in seeing is when is the VAE going to approximate P of x like substantially or meaningfully poorly? So we're looking, and this is what we empirically show with these examples. So let me start with so I have this figure 8 type look density, and then on top of that, what I've drawn is I've drawn the manifold. So the manifold here is, by the way, colored with the corresponding z. So light colors of z are starting over here for z being very large, and as z decreases, it takes you along this manifold all the way over here. So for this distribution, the first condition holds because of the following reason. If you look over here where there are many x's, right, dense region, what you see is that an x over here, for example, could have either been generated by a z over here with a value around 3, or with a z over here with a value around 0. And so because we don't know which one it is, your posterior in this entire region is going to be multimodal. And for this function, you could very clearly see kind of like intuitively that there isn't a function that will give you simpler posteriors, because no matter how you parameterize this curve, the function is always going to get close to itself in some place. And so when the function gets close to itself, you're going to have multimodal posteriors. And so if I were to train a VAE on this, it's going to be forced to make a kind of a trade-off between learning the data distribution and then learning a posterior that's easier to approximate. So what would a VAE do on this? This is the plot that shows you what a VAE would do on this. And I think what the most noticeable thing about it is you see that the manifold over here curls away from this part of the curve. Because if it gets close to it, then all the points over here are going to have multimodal posteriors. And as a consequence of that, you see that the density over here is not quite as dark as it is in the ground truth. And over here, it's not quite as dark either. So we've meaningfully compromised our ability to learn the data distribution. Let me show you what the posteriors look like. So this is like each column represents a posterior for a different x. The top row is for the ground truth model. So you could see that there are many of these bimodal posteriors. And the bottom row is the true posterior of the learned model. So this is not the mean field Gaussian. This is the posterior of the model that we ended up learning. And you see that for most of these, if there was kind of a second hump, the second hump has been made smaller so that there's really just one mode for this distribution. Let me show you a second example. This one is quite different. And here what we've done is basically created a function that's kind of a step function on a circle. And so again, the density here is captured by the shades, and then the manifold is the colors over here. And what you see is that the changes between the modes are very fast, but then this function spends a lot of time on top of these modes, generating these modes. For this, again, you have the first condition satisfied because the true posterior, again, like, if I look at a point over here, it could have been generated by any of the z's over here or any of the z's over here potentially. And so for this, the posterior is going to be kind of like have a high skew, and is actually also going to be bimodal or multimodal. And the multimodality here comes actually from the shape of the prior. And afterwards, I can explain more why that happens if anybody's interested. But anyways, and so for this, you see that also there's no simpler function that can explain this curve, right? If I'm constrained to have a one-dimensional latent space, I pretty much have to go in a circle around all these modes. And so what happens when I train a VAE on it? I get what you have over here, where basically I tried to make kind of like the manifold a bit more identifiable. So if I have a point over here that's generated, instead of it only being able to generate from this mode or this mode, the idea is that now actually could have been generated from this segment of the manifold that has been given more weight. And because it's been given more weight, now you see that the density is smeared between the modes. So it's not really able to capture this. And again, let me show you some posteriors. So each column represents a different X. Top row is the posterior for the ground truth. Bottom row is the posterior for the learned model. And you see that the learned model is literally regularized by the choice of variational family to have unimodal posteriors. So now you might ask, okay, so clearly using a mean field variational family is not so useful for these examples. If I use a richer variational family, will that solve my problem? And the answer is yes and no. So let me just show you first the results and then explain why. On the left here, I've got the true data distribution. On the right, I've got the VAE one, where you see that it kind of smears the distribution over here. It doesn't put enough weight on these chunks of the figure 8. And then in the middle, I have what I get when I use the importance weighted autoencoder, which implicitly imposes a richer variational family. And what do we see for this? We see that it manages to put more weight where the VAE could not. And for this example, it literally approximates the distribution perfectly. And so for these data sets, yeah, you probably should use the importance weighted autoencoder. For distributions for which the conditions, even one of the conditions does not hold, what we've seen is that a VAE will do just as well as IWAY. It won't meaningfully compromise your data distribution. But I will note that IWAY, of course, comes with its own problems and with its own challenges, in addition to noisy gradients that need to have specially derived estimators and computational costs. It also, as I'll show later, IWAY actually under-regularizes your model. And this could be bad in a different way. So we'll get more into that later. So how do these two kind of like pathological examples manifest in real data sets? Each one kind of typifies a different data set. Oh, are people asking question in the chat? Or?
Yes, we just got a question in the chat from Guy Emerson asking how about using a richer prior?
Yeah, I think a richer prior would definitely help with this. I've not done any experiments with richer priors, but I completely suspect that this will make some of these a lot easier. But right now we are studying kind of the most common case in which people use their isotropic Gaussian prior. Good question. Oh, is that another question? No. Okay, so the first data set typifies basically this figure 8 data set typifies a very curvy kind of manifold. So if your data lies on a manifold that's very curly and has a lot of noise, that's when you might expect to see this pathology. And then the second data set, you'd expect to see it when you have kind of regions of low density and high density alternating on your manifold. And I should say that both of these, again, could be alleviated if I'm just willing to learn a mismatch model in any sort of way. So if I'm using a richer prior, probably alleviates the problem. And if I am willing to use a richer family, that will alleviate the problem. And lastly, if I'm willing to even increase the dimensionality of my latent space, that alleviates the problem, as I'll show later. So this is really, but this is really trying to understand when are you going to be able to recover the ground, like a model that is like your ground truth. So far I've shown you kind of that the mean field Gaussian variational family over-regularizes your generative model. And I've hopefully given you conditions that are intuitive to you to explain when this happened. Now I'm going to show you some effects on a downstream task. And for this talk, I'm going to focus on just two of them. The first is learning compressed representations. And the second one is on semi-supervised learning, which relates to our task for our IVF clinic. So for compressed representations, our goal is basically to take our data and then to learn a very low dimensional representation. And so I'm going to denote K as the dimensionality of the latent space, and sigma epsilon is the variance of the observation noise. And basically what I claim is that ELBO is going to prefer models that have a larger latent space than what you would want, and a smaller observation noise, because actually this will help you simplify the posterior. And basically what will happen as a result is that the latent space is now going to start modeling the observation noise in addition to the signal. And so each dimension of your latent space is now going to be less informative, right? Each dimension is now going to be diluted with by having to explain the latent noise. So, and I'm going to do this just for demonstration on the kind of cluster examples from before. So this is the ground truth model with a one-dimensional latent space. These are example posteriors, and you see that they're very kind of crazy looking. On the bottom here, I have what a VAE learns with a one-dimensional latent space. The posteriors are already much nicer looking. And now I'll show you what happens when you learn with a two-dimensional latent space. It's a bit hard to see, but I've visualized the manifold over here. So this is what happens when you take a grid of points in the latent space and translate them through F. And for this model, you get significantly higher log likelihood. And you could see that the posteriors, the two-dimensional posteriors, look really nice. They look a lot closer to Gaussians than before. And so the reason for that is because while in this example, every X could have been explained by only Z's over here and then only Z's in this cluster, so it's very bimodal. In this case, an X over here is just going to be explained by the region of the manifold that's nearest to it. So what I guess I'm trying to say is that we've just made the function more one-to-one, and as a result, the posterior became nicer. Cool. And so now I'm going to bring us back to the motivated.
So Yaniv, can I just a quick question there?
Sure.
Could I also, it feels like I could make a similar statement about if I was using the true likelihood here, that, the true likelihood would always prefer more complicated models because, it has more parameters and it strictly contains, simpler models by just switching off latent variables. So isn't it always true that the true likelihood would also prefer more complicated models? So to what extent is that at play here, as opposed to anything in particular about variational inference?
So if I understand correctly what you're saying, I think that as you observe more and more data, right, then your log likelihood should converge to something that explains your data distribution correctly, and is not necessarily the most complex model.
No, I was just sort of making the comment that the true likelihood for any model with more latent variables will be necessarily larger. The maximum likelihood solution will give us a better likelihood as we increase. If we make a plot, say the maximum likelihood setting likelihood as a function of K, then that would monotonically increase as a function of K here. So
you're saying the more I increase K, are you saying that the more my likelihood will overfit to the data?
For instance, yeah, exactly. Yeah, I mean, it doesn't necessarily need to overfit, but it's just the comment here that if we're trying to tease apart what properties are coming from approximate inference, and what properties are maybe coming from other directions. So one effect which exists here, which is as I make my model more complicated, my log likelihood will increase of the trained parameters. And so, that might be a criticism that we could make at maximum likelihood fitting, for instance, and say, oh, maximum likelihood fitting is bad because it's going to prefer overly complicated models or something like that. So what extent here the fact that the ELBO always selects higher K, for instance, is inherited from maximum likelihood fitting, and what aspects are sort of exacerbated by the fact that we're doing, a mean field variational inference?
Right, that's a great question. I haven't thought about it exactly like that. To me, it seems like if you increase the latent space and reduce the observation noise magnitude, it seems to me like definitely for finite data samples, like that'll allow you to overfit better and therefore get better better log likelihoods. It seems to me like if you were to observe an infinite amount of data, then I'm not sure. Then I would need to think about whether this happens still. But I totally see what you mean, especially in the finite data, finite sample size case. For these examples, I did run with a very large number of points. And so I'm assuming that the effects that I have are not as a function of that. But I also have not studied what happens due to overfitting, so I can't be 100% sure.
Great, thanks.
Sure. Thank you for the question. So yeah, so now I'm going to get into the last task, which is generating counterfactuals. And so bringing it back to our IVF clinical questions, we again want to characterize cohorts in a low-dimensional, human meaningful type of subspace. And our specific goal is to kind of answer what-if questions about the data. So for example, you could let X represent the IVF patient data, so like age, BMI, endometrial thickness, etc. You have Y corresponding to some condition that maybe you've observed a part of the time. So either the patient, let's say, is stressed or not stressed, and you only gave them the survey to some of the patients that came in. And then Z is going to represent other latent variables, maybe capturing like broadly the health of your patient. And the question we want to ask is, if we flip Y, if the patient comes in and they're stressed, and then we want to see what happens if they're not stressed. And so given X, given X and Z, and knowing that Y is 0, we want to basically look at the density of P of X given Z and Y equals 1. And so for that, we're going to use a specific semi-supervised VAE. The idea here is you partition the latent space into two parts, Y and Z, where Y is partially observed and Z is, again, completely unsupervised. And the hope is if you can align at least part of your latent space with the right data, hopefully the Z will also fall into place in some magical way and also be human meaningful. The generative model for this is as follows. You basically have your Z coming from your Gaussian, then you have a Y coming from essentially, and for this, there's a very gnarly looking inference bound.
Hi, Yaniv.
Where basically
sorry, you broke up for a minute there. Could you go again from Y?
Yeah, sorry about that. So Y here is a distribution over over the kind of switch that you want to make, the variable of interest that's partially supervised, and then your likelihood depends on both of these latent codes essentially. And so for this, inference looks as follows. You're given M labeled points, labeled meaning you have X and Y, and N unlabeled points, so only X's. And so to perform inference on this model, what people typically do is they basically add up the ELBO for the unsupervised, the ELBO for the supervised problems, and then they additionally add a discriminator term that actually I'll show causes certain problems when you put it together with mean field variational inference, that basically tries to make sure that at least your labels, Y's, are being used so that you could predict them using your X's on the label data. And for this, we're going to use a mean field variational Gaussian for all distributions. And now we're gonna see what happens. And so the reason why this is specifically interesting for us for IVF is because the IVF data set we have is exactly the data set that's gonna cause us problems when you pair it with mean field variational inference. And so our data set, the thing that's interesting about it is that the patients that are both likely and unlikely to have live birth, for example, they have the same feature correlations. So for example, the more embryos you thaw, the higher the number of those embryos that are likely to survive. That just makes sense, right? If you only thaw one embryo, then you have fewer options for a number of embryos that survives. But then each cohort actually has different feature distributions. So the more embryos that manage to survive, the higher the likelihood that there will be a live birth. So what I'm trying to say here is that basically cohorts overlap significantly in the data space, but actually they have very different distributions on that same shared space. So what this looks like is we're basically going to do something very similar, but with synthetic data. We're basically going to construct a manifold over here, the semicircle, that describes what a realistic patient looks like, because a realistic patient needs to have these kinds of correlations. But then P of x given y equals 0 is going to have one density. P of x equals 1 is going to have a very different density, both on the same manifold. And the reason why this is interesting is because your posterior for your unlabeled data points is necessarily going to be multimodal, because I have to marginalize out the y. So now the question is, if I ignore that fact and I model it using a mean field Gaussian, what am I going to lose? What happens is something that we call functional collapse. And so basically, if you look over here, the bottom axes are my two covariates, my x's. The top axis over here is the z-axis, and those are the two functions that generated the ground truth model that I just showed you. So each cohort has got a different function corresponding to a different distribution. And when I learn a VAE, what you see is that it collapses both functions to essentially be the same function. The reason for that is if you take a vertical cross section over here, right, you look at the number of times that you intersect these two curves, and because here it's 2 times, you're going to have bimodal distribution, and you can't model that with a mean field Gaussian, so it over-regularizes your likelihood to is basically reduced to the same function. So why do you care about that? You care because actually it means you're going to learn exactly the same conditional data distributions. So over here, I have the true data distributions. The top is for cohort 1, second for cohort 0. And then over here, I have what is learned by a VAE. And you see that it learns exactly the same distribution for both, or essentially the same, because the two functions that are learned need to be the same function. So for this, again, you might ask, if I use a more complex variational family, is that going to fix my issue? And the answer is both yes and no. So if you use a more complex variational family, by the way, here's the diagram of what IVAE would do. Your functions don't necessarily collapse to the exact same function. So here you see functions that, sure, they're similar along a part, but they're also very different in other parts, right? So that that constraint is not present anymore. But now your generative model becomes completely unregularized. And so I learned a function over here. You see the one that basically instantaneously jumps over to the side, right? That function doesn't really make sense. And if I were to try to investigate something, I don't know, using any sort of interpretability tools to try to understand what's going on here, I would get very bizarre results. So there's definitely a trade-off to using a more complex variational family that needs to be considered. And I should mention that when y is continuous, actually there are a number of other pathologies that happen that largely have to do with this discriminator term that is added often in a kind of ad hoc way to the objective. And you could check out the paper if you're interested in that specifically. So to conclude, VAEs are super useful for many tasks like learning compressed representations, generating counterfactual data, but when they're used in safety critical applications on kind of numeric data, we really need to understand when they fail, when better inference or more complex inference is worth the trade-offs. And this is at least one step, I hope, in that direction. And then in terms of broader impact, I hope that all these insights and all these toy data sets are going to be used by future people who build VAE inference methods to try to stress test what it is they do. thank you very much for your time. I appreciate it. And I'm happy to take any questions and stick around to chat, hear more about what y'all work on.
Great. So if we have any questions for Yaniv, now's the time. You can just speak up if you have a mic, or you can type your questions in the chat. I think you're muted, Hyde, if you are asking a question.
Hi, Yaniv. I have a question. I'm assuming that it's not asking one. I guess I'm thinking just in general about just adding additional latent variables as a solution, and maybe I didn't fully understand like what's your conclusion about this? Like obviously there's the trade-off of like essentially overfitting, but is it your opinion that this is not like in general a good thing to do?
That's a great question. And I think the answer depends on what you want to use your model for. If you just want to approximate density, then I would say, yeah, increase the latent space to be whatever you want it to be. I mean, be careful of overfitting, of course, but you should basically do whatever it takes so that the posterior is simplest and your objective function is easiest to optimize. I think the problem comes when you want to use the latent codes for a certain task. So if you need to have your latent representation be a certain dimensionality, like you need to be, let's say, small because you really need compression, or you need to be small because you're like, I know for a fact by talking with clinicians the following late features in my data, right? Then that adds more constraints. And so there you need to make sure that when you pick a specific dimensionality for your latent space, that your inference is going to be able to recover that. And so I guess they're kind of two knobs, right? You could either basically say, I want to approximate density, and there you should try increasing dimensionality of your latent space. You could play with fancier priors. You could use fancier or more complex variational family, and you have to just be careful of overfitting. And then there's the task of learning useful latent representations for a task. And there, like you have to, once you know how many dimensions you need for your latent space and kind of what the topology is of your data distribution, then you can figure out what inference choices are going to get you there best. Does that make sense?
Yeah, it does make sense. I think that for the main difference would be for downstream tasks. Like I'm working on some optimization with latent variable models. So having a low dimensionality is useful. One thing that I think is very interesting is the idea of a two-stage VAE. I'm not sure if you're familiar with that paper by Dye and Vip, where they essentially propose learning a VAE with perhaps an artificially high latent dimension, and then freezing that VAE, I guess, sampling the latent codes, and then learning a second VAE that maps those latent codes to an even lower dimensional space.
Right. I remember that paper. That was super interesting. I definitely want to go back and revisit that, but I can tell you that when I was trying to work on this, I didn't try exactly their method, but I've tried other two-step solutions that first, let's say, model density on using a higher dimensional latent space and then does the compression or something along those lines, or first learns the manifold, then learns the density on the manifold. In a similar way to what they did. And for these two examples that I've come up with, I was not able to get anything that looked reasonable. And so I'm not sure if the results are like, I don't know how their method would interact with exactly these toy data sets. But that's another great question.
Yeah, it makes sense. I'm just sort of playing on the idea that you mentioned earlier, that you tend to require more latent dimensions, but each one becomes less informative. And that suggests to me that there'd be some potential for further reduction in some way. Like this two-stage is just one idea, but I think it's a cool, I don't know, just a cool concept.
Yeah, for sure. That is a cool concept. and definitely an interesting idea. I think I just saw a question in the chat as well. Is variational approach sensible for any safety critical application? That's a great question. I think given what I know right now about variational inference, I would not feel comfortable applying it or deploying this in like a hospital. But that is exactly what I think makes it so interesting, and therefore worth studying. Did that answer the question?
Yes, it did. Thank you. I mean, the reason I was asking it is because the variation obviously underemphasizes the width of the distribution, and it's those tails that you often need for utility, for expected utility calculations. That's where the risk often is the worst.
I see, I see.
I had a quick question, sort of following up on sort of question about increasing the dimensionality of the latent variables. So there's this like well-known property that VAE trained models tend to over prune in the sense that they'll get rid of lots of latent dimensions and they won't affect the observed data. And the way I've always understood that property was exactly what you said, essentially, that the trained parameters that you get back from a VAE will try and make your data happy. It will improve your data fit term, your log likelihood, but it will try and return model parameters for which the true posterior is close to your Q distribution. And if your latent variables don't affect your data, or some subset of them don't affect your data, then they sit at their prior in the posterior. The posterior is equal to the prior because the data doesn't tell you about them. And so that is like the mechanism for why VAEs tend to return, simpler models that don't depend on as many latent variables as they should do to the user. So I was wondering whether, how you thought about that, and whether that sort of chimes to your experience. Like I like this sort of nuanced view of what's happening on manifolds, but there are other ways in which the models we get back from VAEs are, too simple, essentially.
Right. I see what you're asking. That's really interesting to think about. So in this example that I gave, if you just increase the dimensionality of the latent space and you keep the observation noise at the ground truth, then what ends up happening is your extra latent dimensions will get ignored. And it will only use kind of the number that was used to generate, assuming that you can, with a mean field variational family on those dimensions, still do a good job. And so I think if you wanted to use that as an approach to kind of like, give it more than it needs and have it select automatically, I think that would work. Or there's a good reason to believe that it would. I haven't tried exactly to see if the model will automatically prune in this example. The problem comes usually with the fact that you don't know what your observation noise is. And so as soon as you shrink the observation noise, what ends up happening is now your latent space starts explaining this observation noise instead. And that's the place where I think my intuition says that you won't get this over pruning, or you may not get it, at least not in these types of examples that I was giving here. Because now every dimension in your latent space is at least going to have a dimension in your observation space that it's going to try to explain the observation noise of. Does that make sense?
It does. I think usually, what we find is that the observation noise actually gets higher than the ground truth value. So you learn a model which is too simple, like it depends on too fewer latent variables. And then the way you compensate for that is that the returned, estimated parameters from the variational bound overestimate the observation noise, and that corrects for the discrepancy between your overly simple model and the ground truth data. So, my mental model for what normally goes on is that you're overly noisy and using too few latent variables. There's nice examples you can do with your linear example. If you take your linear example to start with and give it too many latent variables, then of course, for a linear model, you can't tell how many latent variables you've got because, the linear Gaussian model just specifies a Gaussian distribution on your observed space. There's no way of telling from the observed data what the dimensionality of your latents is. It could be equal or any number above the number of dimensions of your observed space. It would give exactly the same likelihood back. But again, the variational solution is to prune it down to exactly the number of latent variables equal to your observed dimension and get rid of all the extra ones. So it's the same sort of effect at play.
Right. I should say, by the way, in the paper, we do talk a little bit about if you were to use the ELBO to approximate the observation noise to estimate it, again, giving some examples on which this will, like you said, causes you to overestimate the noise, because yeah, that totally happens. Yeah, but that's definitely interesting to see if there's kind of a way of having the variational approach like over prune in a way that is really trustworthy and is guaranteed to give you good properties, so you don't have to deal with this hairy is my model super curvy having it. I mean about the shape should be.
Sorry, Yaniv, you broke up for the last 10 seconds there.
Oh no. I was just saying that yeah, it would be really great to have kind of a more principled, or like I shouldn't say more principled, but to have a very maybe a formal way to characterize exactly how the variational inference kind of prunes dimensions in your latent space. That's something I feel like I'd totally love more intuition on.
Yeah, I totally agree with that. I mean, my general sense is a bug rather than a feature again, although many people will sell it as a bug. I mean, there's a paper by David McKay. So I think the properties that you talk about are true of variational inference in general, that wherever we use variational inference, the sorts of models that we're going to return are going to be simpler than they should be, in the sense that the true posteriors corresponding to those models will have properties that are inherited from our Q distribution, like they factorized posteriors or whatever. And so there's a nice example of David McKay in for Gaussian mixture models, where you've seen one data point and you want to make an inference on the parameters for an underlying Gaussian mixture model. And the inferences you get back after seeing one data point is that it completely prunes out one of the components. It says the mixture proportions for one of your components is 0. So there's a mixture of one Gaussian. And of course, that's nuts after seeing one data point, because after you've seen one data point, you could have one or you could have 100 components in your mixture of Gaussians model. You just can't tell from seeing one data point. It had to come from one component. And so this is another example of like being biased towards overly simple solutions, which make your structure in Q sort of more correct, essentially.
That's super cool. If you actually could paste a link to that paper in the chat, I would really appreciate that. I would love reading that.
Yep, yeah, I can paste those.
Thank you.
Great. If there's no more questions at the moment, I might stop the recording, and then we can continue with a more informal discussion afterwards. So thank you very much for your talk, Yaniv, and I'm looking forward to having a nice discussion with you.